Okay, so I will begin now.
Yeah.
Okay, so thank you for your attendance. Today we would like to present you the color of mixed pigment. I'm Adithep KAWINKIJ and I'm with Basile MADDALENA, and we are doing this project under the guidance of Mathieu Ebert. So in cosmetic, predictive model of color of a product appearance is an interesting concept in terms of product aesthetic design and development. Usually, most cosmetics are mixtures of four primary colors, including red, white, yellow, and black. You can see, as you can see on the slide. However, predicting this color of mixture using the primary colors is difficult and might require optical models. So in this presentation, we would like to report you the methodology and the result of our attempt to establish this predictive model of the mixture of material. So these are our objectives. So the first objective is to extract the scattering and the absorption coefficients of the primary materials on the drawdown card. By the way, drawdown card is kind of black and white paper with the sample on top, as you can see on the slide. And the second objective is to establish a predictive model of the color of the mixed material using the scattering rate and the absorption coefficient of the primary material. So the first step in our methodology is to measure the primary material using the spectrophotometer. As you can see on the slide, this instrument is called X-Rite CI 7800, which is funded actually by Manutech-SLEIGHT Graduate School, and it is located in the photometry laboratory of the Institute of Optics in Saint Etienne campus. We use this spectrophotometer to measure the reflectance factor of the primary colors on the dollar card with this illumination. Then we use our machine to calculate the scattering layer absorption coefficient using the inverse Sanderson and Kubicaus model. And we inject this measurement in the color mixing model to obtain the predicted scattering and the absorption coefficient of the mixed color. After that one, we put it back in the optical model, the Sanderson and the Kubicaus, in order to get the predicted reflectance factor of the mixed color of the mixed material. Sorry. Now we can already compare it with the real measurement of the mixed material. We can do it in the CAE LAB color space, which in which the distance or error can be measured. At this point, the whole problem, our problem become an optimization because we try to reduce, we try to actually minimize the color distance or the error of the model by playing with the color mixing model.
Yes, thank you, Adithep. So first, what we have done is that we have measured all the reflectance of the periodic pigments, so the yellow, the red, the white, and the black one, with the spectrophotometer. And we have measured the reflectance of the four pigments with 3 different layer thicknesses on 2 different backgrounds each time. So there is the black and the white background, as you can see on the image on the left. For example, at the right side, you can see the 8 curves of the yellow pigments, and all data have been transformed for confidential reasons according to the will of the company we work with. So then, from the previous measurements, we can deduce using Kubicaus and inverse Sanderson model the scattering and absorption coefficients denoted by K and S respectively for each layer thicknesses. Theoretically, all the K and S should be the same and should not depend on the thickness of the layer. However, the results are not, as you can see on the graph. So this is the limit of Kubicaus model. As the thickness increases, the material becomes opaque, and there is no difference between the appearance on white and on black background. Thus, the K and S cannot be measured properly. I just want to remind you that the aim of the project is to search for a model that predicts the color of a mixture, knowing the proportion of each pigments that compose the mixture. So first, we have tested an intuitive model that is linear. We call this model the B-Lambert-Bugger-Law. And this model just tells you that the K and S factors of the mixture can be determined just by calculating the weighted sum of each K and S pigments factors that compose the mixture. As you can see on the figure, using this law, the difference between the predicted and the measured reflectances are significant. So to solve this problem, we have tested another model that take into account the scattering interactions between each pigments with a new parameter. This model is called Yule-Nielsen transform. And we can note that this model is more accurate than the other one because the reflectance difference between theory and experience is smaller than before. So we have simulated and measured the color of two foundations using first Biot-Lambert-Bugger law. And we can see that there is a small difference for the foundation 1 and a big difference for the foundation 2. And using the Yule-Nielsen transform, you can see that there's really no difference for the first foundation with between predicted and measured color, and there is a very small difference for the foundation 2. So to conclude, we have established the procedure to predict the color of a mixture of a foundation, and we use optical models, and the result seems to be satisfactory using the Yule-Nielsen transform. Thank you all for your attention.